Me, take really good notes because you're not going to find this in your book. This is kind of an assumed already skill. So I'm going to start out with that, and it's going to build kind of on that activity that we did yesterday. So we're going to talk about domain and range for just a second. This is 2-3, but we're going to do a little digression here. All right. We should be well versed in domain and range at this point after yesterday, right? Can everyone adequately describe the domain and range of a graph? Let's see. You don't have to know how to graph this. I just want you to, if this point is 2, 2. That looks terrible. Looks like it's going to hump. There we go. What is the domain of the graph in green? Domain. Left to right.
X is greater than 2.
So if you're telling me X is greater than 2, then you're saying that there's only graph this way.
X is greater than 1 or less than 3 or 4. 4 is a 4.
So you're saying that the graph never goes past this line or this line?
Oh,
We can move that.
the 3. X
3.
is all the
1 grabbing X is greater than 2.
How do you know?
It's kind of creeping out ever so slightly. So we're talking infinite type things here. We're not talking about just the screen because I have the arrows on the end. So we're talking about.
So we don't even need to restrict it.
It's not restricted at all. It's forever and ever and ever. So X is all real numbers. And I just want to make sure because I'm going to teach you a new way to write this, which is the new part today. How about the range?
Greater than 2.
Yes. Range is Y, right? Yes, ma'am.
So, like, if it was on the computer, I know yesterday, if it ends with, like, a point, then it's not, like...
That's restricted then. Right, correct. So yesterday you had things that might have looked like this, right? And so if this was 1, 2, 3, 4, the range, the domain would be from -4 to -1.
And that's because that's a line.
It's a line and it's restricted. It's a segment. It's a line segment, not a line. Because if it did that, suddenly we've changed to all real numbers. You see the difference? Okay. Let's do one more. We're going to kind of make some real life graphs here.
Like a mood swing?
It's a cubic, actually. We'll get to it. What is the domain? What's the domain here? It's slightly going out. All real numbers. What's the range? There's no restrictions on X or
It's
Y.
moving down and out and up.
One more. All real numbers. The domain is all real numbers, right? There is no restriction on X. How about the range?
Is the range always going to be all?
No. If there is ever a restriction, if it ever stops left to right, if there's something it can't be left to right. Think about that shading on that activity yesterday. What stopped it is because there were endpoints on it.
Okay, so if there's not arrows,
Well, I'm coming back to that. What if my graph looked like that? then there's a domain restriction, not a range restriction. Because I'm talking left to right for domain. So whatever this point is, think about your shading, it would be shaded that way.
But then there wouldn't be a number at the end of that.
No, it'd go on forever, correct.
So how would you write that?
Maybe
Oh, just no.
if it looked like that, we'll get to some graphs that look like that. That has domain and range restriction on it. Come back to this one. All right, so domain, we know all real numbers. Range is what we're looking at. And so you said what? Okay, so this is -2 on y, this is 3. So we know that what?
It could be like x.
It could
or
be-
y is like not equal to whatever I just add is greater than.
Just tell me what it does equal.
Y is less than or equal to -2.
Yes.
And y is greater
And-
than.
Okay, so I said it, right?
Yeah.
Greater than or equal to negative. So you can do that, you don't have to put it.
Two parts.
Can
Now, we're not going to use writing. This is a very, very elementary way of writing domain and range, what we're doing with the inequality signs. I'm going to teach you a new way. It shouldn't take but just a little bit. We'll see. All right, I'm going to teach you interval notation. It's fun. So from this point forward, every graph that you have, you will do domain and range on, and domain and range will be done in interval notation. Yay! It's so much easier than inequalities. It is so much easier, so much better. All right, I want you to think about, let's think about one of those inequalities we had. What did we have? Y is less than or equal to negative, was it 2 or 3? 2. Okay. On a number line, that's going to put me at -2 with a solid dot going to the left, right? Now I want you to think about this number line. If you go on forever to the left, what can I indicate forever that way? Forever negative? Infinity. I'm going to let forever this way be negative infinity. Forever the other way be positive infinity. Okay. I'm also going to tell you that should you see less than or equal to or greater than or equal to, so if I'm talking inclusive, I want you to think bracket. But if you see exclusive, I want you to think parenthesis. Interval notation is exactly what it sounds like. It's a way to write an interval of numbers to indicate inclusive, exclusive, and give a range of numbers, basically is what it's saying. So if I want, and you always have to start with interval notation, smallest to biggest. So if I am looking, and by the way, if I'm describing infinity, do you think that would be inclusive or exclusive?
Inclusive, because it's all of infinity.
Think about what it means. It's all of infinity, but can you actually be infinity? It's kind of a conceptual thing, right? So if you ever talk about infinity or describe it in interval notation, it gets a parenthesis every time. Because you can't actually be infinity, right? It's just telling me it goes on. Does that make sense? A little bit? Sort of? Okay. All right, so I want you to look at my number line, look at the inequality, and tell me if I'm describing y. What's the smallest, because it goes from smallest to biggest, what's the smallest that y can be? Negative infinity. Smallest, right? The smallest is negative infinity. Do we all agree? Because I can't actually be negative infinity, I'm going to put a parenthesis. Okay? Interval notation is made up of two values, so you do a comma, and then it goes up to what?
-2.
-2. Does it include -2 or not?
No.
Wait, yes. Yes.
Yeah, but I thought that's exclusive. Okay.
That means inclusive.
Yeah, but in your parentheses, wouldn't you put it in brackets then?
So I would put it in bracket, right? I would put this in bracket. Only you. Yes. You can have anything on either sides. Okay. This little two-value expression here is the same thing as the number line that is above it. It's saying y can be anything from negative infinity up to 2, inclusive. Let's try another one. What was the other part of the range? Y is, let's just say it's greater than 3 instead of greater than or equal to 3. How might I write that in interval notation? That's exactly right. Open dot. The smallest it can be is 3. It's a parenthesis because it does not include it up to positive infinity, and again a parenthesis. Yes. It was a bracket around the -3. Yeah. What if, yeah.
Why is on the one before, what was number 2, the y number, and why was 3 that?
It's smallest.
Yes, it's not an x and a y, it's smallest to biggest. Yeah. Don't think of it as a coordinate because it's not what it is. Infinity can never be bracket. Infinity is always exclusive.
Why do you have a bracket on this one?
This one is just greater than. The other one was less than or equal to. If it's equal to, it's bracket. What you mean? We would just, because you write range equals and then you write the interval notation. Yes. How about if I want between two numbers? We did a lot of betweens yesterday, right? Let's say my range was something, or my domain, it doesn't matter. Let's say it was between -3 and 5. It's actually way easier than what you probably think it is. What's the smallest x can be? Inclusive, exclusive. Does that mean bracket or parenthesis? Parenthesis. That's okay. If you can describe it in inequalities, you can describe it in interval. Here's where it gets a little harder, and not really harder, it's just that last one that we did, right, with the range, had two parts to the range, right? It was, what was it? Y is less than or equal to negative and, okay. Here, with interval notation, if it's not between two values and it goes off, and this is when you start thinking about your compound inequalities, whenever you had ands and ors. When it looks like this and it goes off in different directions, you can join two intervals together in interval notation. And to do that, you just use a U, okay? So what you're going to do, if you think about this, if this is -2 and this is 3, this goes this way, this goes this way. How do I describe? Let's just start going. Let's just go smallest and go up. What's the very smallest it can be? Negative infinity. Then I go up, up, up until I hit -2, right? And I stop. Do I stop and include it or exclude it? Include it. Now I skipped some space. So what I need to do is join it with a U to union. I don't know if y'all remember union and intersection of sets. Okay, I don't think they teach that anymore for whatever reason. All right, but I union it, I combine it, and make it one with the next. So where does it pick back up?
Inclusive 3.
Bracket 3, inclusive 3. Up to what? Infinity. It's not bad, right? It's just a new way of writing what you already know.
I'm just confused on the brackets.
Brackets, if there's a line under it or it includes the point, it's a bracket. If it does not include the point, it's a parenthesis. Think closed dot, open dot for. Let me test your knowledge. U just joins two pieces together when you know that like on that last one we did, the range had two parts to it. There's two parts, and I needed to combine that. So you union them together to combine it. Yes, good question. All real numbers, if it's everything, it's actually negative infinity to infinity. That's all real numbers. So to say everything, you do negative infinity to infinity, which will come up a lot. Look at this graph. Describe the domain and range of this graph in pink. Domain. Think about that shading yesterday, okay, and what all it can be. So you're right. Don't give it to me like that. What's the smallest x can be? 2. Parenthesis or bracket? Is it? I don't know. There is a point there. It includes it, so it's a bracket. What does it go up to? Because you can't actually be infinity. Like you can't, it's kind of conceptual. How about range? 1. How would it change if my graph was the blue graph instead of the pink graph? The domain remains the same, right? And the range is a little bit different. What happens to the range? Which one? Range is still restricted if it's just the blue, not the pink.
Oh, if it's
just the blue. Smallest to biggest, negative infinity to 1. No, because it's going to the right. Domain is left to right, range is bottoms up. Does that make sense to you? A little bit? You will get so used to it. It really will. But we're going to focus on domain and range.
That's like a reflection, right?
Yes, it is. It's absolutely a reflection. Good job. All right, let's talk about some in behavior. Now we're jumping into lesson 3 where we start. But they'll ask you for domain and range, and I wanted to make sure that you were in the right. I don't want to start you off on inequalities with domain and range. I'd rather you know the right way to do it to start with. All right, in behavior. This is probably my favorite. In behavior is exactly what it sounds like. It tells you what the end of the graph is doing. Okay? It's just written in a mathematical sentence. That's the hardest part, is understanding that mathematical sentence. All right, so if I've got a graph, and we'll just take a line to start with. Plain old line. We'll say this line is f of x. Because we know that that is just what? Function notation, and it's y, right? Okay. If I want to describe the ends of the graph, how many ends do you see?
None.
Right?
Ends?
Not like stop ends, but how many directions does it go off? Maybe I should say that differently. 2, right? It goes off in 2 different directions. And every graph you do, it's going to have to, I mean, we're talking about functions, they're going to go on forever. We're not talking about discrete functions. We're going to be talking about continuous functions. So they're going to go on forever. So they're going to have 2 ends that we're going to look at. So to describe these ends, here's what we do. We need two mathematical sentences to describe the ends. One of them is going to describe this end, and one of them this end. Okay? I'm going to use an arrow, and this arrow is going to be read as approaches. Okay? So it's getting you ready for limits in pre-cal is really what it's doing. All right. My first sentence. I'll describe the right side of it first. As x, so this is my x-axis, this is my y-axis, right? As x approaches positive infinity. So tell me what you know about that. What does that mean as x approaches positive infinity?
As it goes on forever.
Forever which way?
To the right.
To the right. Do we all understand why that's to the right?
Oh, because it's.
So this is saying as x approaches positive infinity, which means, look at the right side of the graph. Tell me what the right side of the graph is doing. As x approaches positive infinity, what is f of x doing?
Increasing.
So would f of x be approaching positive or negative infinity? Positive, because it's going up. Now we said there's two ends. That was the right end. How do you think I might describe the left end of the graph? As x approaches negative infinity, what is the graph doing? What is f of x doing? That's exactly right.
What if it was like this
I'll show you. I'll show you. Okay, so understand how we read this and what this is saying. The right side of the graph is going up, the left side of the graph is going down. Okay, it's just a mathematical way of saying that. That's all it's doing. I got that? Let's take my favorite little cubic function I keep doing. Describe the end behavior of the graph. Okay, so we have two ends we need to describe, right? As x approaches what? You can start with either one you want. We'll start with positive infinity, which means which side? The right.
What? Oh, okay.
Where does x get bigger? To the right. So I'm looking at the right side, right? This is x, this is y. So as I look to the right, what is the graph doing? On the right side of the graph, is it going up or is it going down?
Down.
It's going down. How do I say that it's going down?
Negative.
That's exactly right.
Would that be the same thing if it was a negative sign?
Yes.
Wait, how do you tell which side?
Positive, so when x approaches positive infinity, so this is x, right? So as x gets bigger, so I'm talking about the right side of the graph, it goes down.
You see, when it says that, you're not looking at the line, you're just looking at the graph.
Yes. Yeah.
That's
F of x means y. It's the picture of the graph itself.
so then.
But yes, you can equate that to
I like
range.
the snow guy.
That's okay. Am I done with end behavior? No, because how many ends does it have? 2, so I better write 2 sentences. Now as x approaches what?
Negative.
Negative infinity. So look to the left. What is the graph doing on the left?
Rise.
Positive infinity.
Positive infinity.
So that means it's left going up.
Yes. Yes.
What if it's horizontal way? So you have to pay attention to the
I'm fixing to do
axis.
one like that. Good job, Callie. You're just jumping right ahead.
So that means you have to pay attention to like the axis.
Mm-hmm. Yep, absolutely. Do a couple more. Of course, I'm going to throw some tricky ones up here.
Just give
Describe the end behavior of f of x. Okay.
It's not f of x function. F of x is x.
Just got slope of 0. Okay. As x approaches positive infinity. Who said it? Good job. You're right. It's always going to equal 3. Y always equals 3. That's the line y equals 3. F of x equals 3. It doesn't matter whether it approaches it from the right or the left. It's going to equal 3. Right? It's not approaching anything. It is 3. It's not getting very close to 3. It is 3. So on the left side, it's going to be the same thing. As I look to the left, it's still 3. It's always 3 because that's the equation of the line. Does that make sense?
Yeah.
Does it make dollars? Oh my goodness. Okay. One more.
Yeah, she had to explain the dirt. She was like, I don't get it. She's like, what?
How much sense does it make?
But if it's vertical, it's almost vertical. So it's just gonna be 1?
Vertical line's not going to approach, x is not going to approach positive or negative infinity. That's not a function either.
So you never have that vertical.
Woo, this is a quartic. A quartic. We'll get to all that. We'll get. Oh, by the way, before you do this one, looking at the graph, oh, no, not a good one. Okay. Just in case you need some points in there for whatever reason you might need them. We're going to do 2 things with this graph. Thing number 1. Describe the end behavior of the graph in pink, please. No, you still got to do it twice because it's still 2 ends. So as x approaches positive infinity, what does the graph do? It's going up really fast. That's right. How about the other end? Same thing, right? But it's just as x approaches negative infinity, the graph is still going up. Okay.
Negative infinity because it's leading, right?
Correct. Well, negative infinity because what's negative infinity?
This one on the left because it's leading.
It's just saying to the left. Yeah, it's still going to the left. Which brings me to my next point. Well, yes, but that doesn't have anything to do with left to right, because left to right, they're still both going up. But that's going to have something to do in just a second. So, now I want you to take the same graph, and I think you'll see why I put the points on there now, and describe the domain and range of the pink graph. What's the domain of the graph in pink? Domain is left to right. Negative infinity to infinity. What is the range of the graph in pink? Good job, y'all. Give yourself a pat on the back if you got that. -2. Remember, okay, so here's what I always say. Domain is left to right. What's the furthest left and the furthest right? That's domain. Most of the time you're going to be negative infinity to infinity for our introductory functions. We will get to a lot that are not, however. Your range, I always say bottoms up. Lowest it goes, up to the tallest it goes. Okay? Very lowest thing it goes to is -2, and then it goes up to infinity. Goes up forever. Bottoms up. So from the lowest point, the very bottom point on the graph, and then go up. So does it stop anywhere from there up? No. And if it faced down, then you would be, the bottom would be negative infinity up to whatever point it
Wait,
stops.
so for domain, why wouldn't it stop at negative?
Because these arms up there are just kind of easing out as it goes up. For the range, yeah. Huh? I just put it up there to be Miss McGee. No, you're looking at the graph overall. Remember whenever y'all had that one where you had shading like this and then shading in the middle, and I said you don't need that middle shading because you're being redundant. You don't need redundancy. If that includes it, you don't need to go back. You're looking at the graph overall. Yes. We'll get there. We'll get there.
Today?
Possibly. Today, not quite as much, but maybe. All right.
What? Not quite as much, maybe.
Yeah, I don't know how far we're going to get today. We're trying. All right. Let me talk to you for just a minute about extrema. What?
Is that a terrorist group?
Yes.
When we get done with function analysis, you will have 7 to 8 different pieces of analysis that you will do. You have just learned the first couple being domain and range and in behavior. Okay. You will, by the time we're finished with these functions, and there's actually 8 or 9 now. You will be able, and symmetry is another. Okay. You will be given an equation. You will graph it. And you will tell all these things about that function. Okay, so that's what we're basically doing is we're leading up to that. So I'm taking you slow through all the steps of function analysis here. One little thing at a time. All right, let's talk about extrema. They're everybody's favorite. Is it going to be what? You might need a little more room than that. Lots of graphs. There you go.
Do we have to graph anything?
Yes. All right, extrema. Here's what extrema are. Another word. Let me give you kind of a definition of it, and you see if you can figure out what extrema are. I'm gonna say extrema, aka, you know what that means?
No.
Also known as.
Turning points. Inflection points. Change of direction point. What is that? Yes. So everybody's doing it with your, yeah. Let's take that same graph that I just showed you. It looks something like this, right? That's exactly right. When it changes direction, if you take your pencil, I'm going down, 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 baby, down. Oh, it stops right here. It stops. It stops going down. It's not going any direction. It turns and it starts going up. The point where it changes direction is an extrema. Okay, it's an extreme point. We have 2 types of extrema, and then each one of those has 2 types. So. And it's not, no.
I like that.
We have maximums. Yes. And minimums. And under these maximum and minimums, you could have different kinds. You could have what we call an absolute maximum. Or a relative, which is sometimes called a local maximum. So here's what it means. Let me finish writing this. relative, local. All right, so they happen at, and we call these a lot of times in like a parabola, that'll be the vertex, okay? An absolute max or min is absolutely the highest or lowest point on the graph ever, ever, ever. Well, yes, that's the extrema. But as far as the difference in these two, absolute means if it's an absolute maximum, it is the highest point on the graph. There is never any point ever, ever, ever on the graph that it goes any higher than that. So if you look, how many maximums do you see in this picture? One, right? The arrows don't count. Arrows don't count because it's not changing direction there, right? That's just indicating that it goes up forever. I see one maximum. Is it an absolute?
No.
Why?
Because the arrows are higher.
These ends are higher than that, so it's not absolute. But it is a maximum because it changes direction right there. So it's relative.
Okay. So it has to be going equal positive. So the right one is the higher.
So the other two, exactly. So maximums happen at the top of mountains. Minimums happen down in the valley. Okay, so how many minimums do you see? Two. Minimum. What kind of minimums are these? This one is relative. Why? Because there's a point lower on the graph. But this one is absolute because there is absolutely no other point that goes below that one on the whole graph. Does that make sense?
Yes.
I told you these were easy. Yes, our calculator is going to do that for us most of the time, though. One other type of critical point that I just want you should know, and your book kind of assumes that you know this, but I'm going to assume that you don't. Zeros. What are zeros? What's 0 at a 0?
Nothing.
Okay, clearly we don't know. Zeros are where it crosses the x-axis. These are very, very, very important points. We'll do a lot with them. It's where your sign changes from negative to positive. The sign of what? The sign of y. The sign of the function itself changes from negative to positive or positive to negative. Okay? I should say sign changes. Just sign changes. I'm going to just say sign changes. Yeah. Okay? So, as you look at graphs, you're going to be doing several things with them. You're going to be finding the extrema, the zeros, the domain and range. I think that's it.
So the zero is literally just like
Yes, same thing. All right, so as was asked, let's see what a word problem looks like with this. The average cost of a theater ticket at the local cinema. Ooh, I gotta copy this. Let me do this one. The table and graph represent the balance in Frederica's savings account over a year. So I've got month. Balance. This goes up to 12. Shh. Month. All right, guys, y'all stay with me. You wanted a word problem. I'm giving you a word problem, but it takes me a while to set it up. 11, 12, 13, 13, 14, 12, 13, 14. This isn't in your book. All right, there's her balance in her savings account. When we graph it, we're going to start at 700. We'll go up 8, 9, 10, 11, 12. I need to go up to 15. Okay. All right, this will be in hundreds. So if you're not graphing this, this is fine. All right, month 1 is 1100. What? 2 is 12. 13, 13, 14, 12, 13, 14. Ooh, what happened that month? That must have been Christmas. 9,000, 11, and 12. So it looks something like this. Yeah. All right. Woo! There we go. That was a quick graph, and but you get the point. So your directions would be use the table and graph to estimate the extrema for this function. Oh, they're going to be nice and graph it for you. I'll probably make you graph it yourself because I mean. Okay, explain the extrema in context of the situation. What extrema do you see? 900 is definitely, what is that? So what's it? Absolute minimum. Explain what that means in this situation. It's her lowest bank account. The lowest she ever had over the course of 12 months was $900. The highest, the most she ever had, exactly, it occurred twice. So is it absolute or relative? Mm-hmm. Can't have two absolutes. Okay, so these are relative. So the most she ever had was $1,400, and it happened not once but twice. Let's see if you understand. What's the domain here? One to 12. Y'all got that? Parentheses or brackets?
Bracket.
Good job. There's actually a point there. Because there's actually a point 1 to 12, so it would be inclusive. Yes. Inclusive, exclusive. Smallest amount she ever had was 9. The biggest amount she ever had was 14. Tell me what you think. In behavior, domain, range, and extrema. Okay. Do what?
Watch the video again.